Hi everyone, this is the third in a series of 3 videos. It's going to cover the content for differential calculus for the International Baccalaureate course Maths Standard. So in this video we're going to go through increasing and decreasing functions. We'll look at stationary points and inflections. Then we're going to look at the study of kinematics, which involves displacement, velocity and acceleration, and then we'll finish off with rates of change and optimization. Okay. Recall that the derivative is the gradient of the tangent to the curve, y equals f of x, and for that reason it's called the gradient function. And this is really important. If you remember that the derivative is the gradient of the tangent, you can actually use that fact to make sense of the problems that you're given. We also need to remember a few things about gradient, namely that uphill the gradient would be positive, downhill would have a negative gradient. If it's flat, the gradient or the slope is 0. And if it's completely vertical, it's approaching infinity, so the slope or the gradient is undefined. So we can actually use those facts to figure out whether a function is increasing or decreasing. So if f dashed of x is greater than or equal to 0 for a particular domain, then the function is said to be increasing. If f dashed of x is less than or equal to 0 for a particular domain, the function is said to be decreasing. So let's have a look at this function over here and figure out where it's increasing and decreasing. Let's take this section first. All right, what we've got to do is draw in the tangents because the gradient of the tangents is the first derivative. What's the gradient of these lines here? Would you agree that they're all positive? So because the first derivative is positive, then this part of the curve is increasing. Coming down here, would be decreasing because the gradient of the tangents there would be negative. And then finally coming up here, it would be increasing again because the gradient of the tangents is positive. Here's an example. Show that the function f of x equals 3x plus 5 is increasing for all real x. Now this is called monotone increasing, when something is always increasing, also sometimes known as monotonic increasing, but they mean the same thing. If you think of what a monotone is in music, it means the same note being played over and over. It's kind of the same here as well. So it means that for the entire domain, it's going to be increasing. We could also have monotone decreasing for that matter. What we've got to do, however, is find the first derivative and show that it's always greater than 0. It's pretty easy. The first derivative is 3. 3 is always greater than 0. So since 3 is greater than 0, f of x is monotone increasing for all real x. Here's a harder example. Find the interval or intervals where f of x equals x to the 4th minus 4x cubed plus 5 is decreasing. Alright, so we're going to begin, like we did the last one, by differentiating. Now we need to solve the derivative, find out when the derivative is less than or equal to 0. And we're going to need to factorize and then do a sign diagram. So let's begin by factorizing. Now to solve this less than or equal to 0, we need our critical points. So remember, they're the solutions of this equation equals 0. So x is 0 is one of them, and x is 3 is the other. Draw up a number line. We're going to test in here, and in here. Let's begin by testing -1. Just going to work out the sign here. I don't need the value. So this is a product. I'm going to multiply this by this. So let's figure out what the sign is of each of these bits. If I put -1 in here, I get a positive. If I put -1 in here, I get a negative. Positive times a negative is a negative. Now let's test 1. Putting 1 in here, I get a positive multiplied by a negative. Again, a positive times a negative is a negative. And finally, test x equals 4. Putting 4 in here, I get a positive. And putting 4 in there, I also get a positive. And so that will be positive. Okay, so it seems from our diagram that it's going to be decreasing all through here. But I have a question. Do I write that as 2 intervals or as 1? And I've chosen this question for a reason, just hopefully to clear up any misunderstanding. The definition says that when the derivative is less than or equal to 0, then the function is decreasing. It's true that here it is equal to 0. So when I put 0 into here, I get 0 take 0, which is equal to 0. But just because it's 0 here, does that mean it's not decreasing? If you think about it, coming from negative infinity here, it's going to be decreasing all the way through here. Even though it goes through 0, it's still decreasing. And in fact, when we have a look at the graph, that's what it's showing us as well. So decreasing, 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 goes through 0, decreasing, decreasing, decreasing. So we actually do just write it as one interval. And we're just going to write x is less than or equal to 3. So let's move on to stationary points. If the gradient of the tangent at a particular point is 0, then the curve has a stationary point. So that means that at that particular point it stops. It could be one of two things. It could be a turning point, so it turns around, it stops and turns around, or like that. Or it could be what's called a stationary inflection, and that'll look like this. So it stops, but then it keeps going. Now, a stationary inflection, the curve will change its concavity, and that's what this is what concavity means. This is concave down, and this one is concave up. We're going to do a little bit more on this later on. So let's have a look at the stationary points on this particular graph. So we have a local maximum at negative 1.2, so up here. It's called a local maximum because it's not the absolute maximum. See how this curve keeps going off to infinity? But at this particular part here, it's a local maximum. So this would be like not the tallest mountain in the world, like K2. Okay, it's still a maximum. What else have we got? We have a stationary inflection here, sometimes called a dog leg. Don't know why actually. Stationary inflection at x equals 0. And we have a local minimum at x equals 1.2. So again, it's not the absolute minimum because this goes down to infinity or negative infinity. So local minimum, stationary inflection, local maximum. At all of those points, the derivative is going to be equal to 0. Here's an example. Find the stationary points for f of x is equal to x to the power of 4 minus 2x squared. So we are going to differentiate. We get f dashed of x equals 4x cubed minus 4x. Let's factorise that and put it equal to 0. And we want to solve this. So 4x multiplied by x squared minus 1. You could further factorise that into x minus 1, x plus 1 if you wanted to. But our solutions are going to be x equals 0 and x equals plus or minus 1. Okay, that's not the end of the story because we've asked for the points, which means we need x and y. So in order to find the y coordinates, we substitute these back into the equation up here. A common mistake is to substitute it back into here. That's always just going to give you 0. So we substitute them back into the curve so we can find the y coordinates. Putting 0 in there, we get 0, and plus or minus 1 are both going to give us the same answer. So 1 to the power of 4 is 1, take away 2 times 1, which is negative 2, so 1 take away 2 is negative 1. So we have our points 0, 0, 1, negative 1, and negative 1, negative 1. There's our 3 stationary points. In the previous example, we found 3 stationary points, but we didn't say what type they were. They could have been maximums or minimums or stationary inflections. We're going to learn now about the second derivative, f double dashed of x, which is going to help us determine the nature of the stationary points. So the second derivative finds the gradient of the tangent of the first derivative. In other words, it finds out how much f dashed of x is changing as x changes. Now, if the second derivative is greater than or equal to 0, then the curve y equals f dashed of x, so the first derivative, must be increasing. And that means the original curve is going to be concave up. It's going to look like this. If the second derivative is less than or equal to 0, then the curve y equals f dashed of x is decreasing. And that means the original curve is going to look like this. It's going to be concave down. And then finally, if the second derivative is equal to 0, then the curve of the first derivative must be stationary. And this is called an inflection or a change in concavity. So it's going from concave down to concave up or the other way around. There's 2 types of inflections. We're going to go through those shortly. There's ones where they just change in between. So somewhere like here, where it's changing from concave down to concave up, or there's those dogleg ones like this. Let's have a look at this curve here, and we're going to complete this table for f of x, f dashed of x, and f double dashed of x. We're going to say whether they're positive, negative, or 0 in value. So we're going to start with the actual curve, first of all, which is here. And so we're going to have a look at this point here, A, and decide whether f of x at this point is negative or positive. Now, that's just the y coordinate. Okay, it's -2, so it's definitely negative. B, it's 0. C, positive. D, 0. E, negative. F, 0. G, positive. Hopefully that was fairly easy for you. Okay, it's just the y coordinate. Now we want the gradient of the tangent to the curve. Or is it increasing, decreasing, or stationary? So here it's going up, isn't it? It's increasing. Here, still increasing. See, going up. Here, stationary. Here, now, it's coming down, so it's negative. Stationary. Here, it's positive because it's heading upwards, it's increasing. And G, it's also increasing. All right, lastly, we're talking about concavity. Now what you can see here is that this section here is concave down, and this section here is concave up, and that point there is going to be an inflection. I know that you're kind of used to a stationary inflection. This is a different type, we'll get to that, but this is the change in concavity here. So all of these sections are concave down, which are negative, and all of these are concave up, except for D, which is 0. So negative, 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 0, positive, positive, positive. Okay? Sketch the curve f of x equals x cubed minus 3x squared plus 5 by finding the stationary points and inflections. Okay, firstly, differentiate. Factorize and put it equal to 0. Okay, let's solve this. X is equal to 0 or 2. Remember, we don't just want the x values, we want to find the points, so we need the y coordinates as well. Sub back into here. 0 into there gives us 5. 2 into here gives us 8. Take 12 plus 5 is equal to 1. So our stationary points are 0, 5 and 2, 1. Now we're going to test the nature of the stationary points using the second derivative. So this is new, we haven't done this yet. So let's find the second derivative. Okay, remember, if the second derivative is negative, it's concave down. If it's positive, it's concave up. So we can tell whether it's a maximum or a minimum by substituting in. We only need to substitute in the x value, so let's put 0 into here. So f double dashed of 0 is equal to -6, which is less than 0. Therefore, it's concave down, and so it's a maximum. Now, this seems a little bit counterintuitive. It's concave down, but it's a maximum. So if you just think about maximum, and here they're back the front. So either remember it that they're back the front, or go through this part here, and that'll make sure you get it right. So if it's negative, it's concave down, which is a maximum. Let's do this one now. Put x equals 2 in. So putting the 2 into here, I get f double dashed of 2 is equal to 12, take 6, which is 6, which is greater than 0, therefore it's concave up, therefore it's a minimum. Okay, so there's our 2 stationary points that we've found. Now we want to find the inflection, and that's going to be the second derivative equal to 0. Okay, so solving that, we get 6x minus 6 equals 0, 6x equals 6, x equals 1. Again, we want to know it as a point, so we need to know the y coordinate. Put 1 back into here. It's going to give us 1, take 3 plus 5, which is 3, and so we have an inflection at 1, 3. Let's have a look at what we've done so far. We've found the first derivative and solved it equal to 0 and found our 2 stationary points. We've then determined that this one's a maximum and this one's a minimum. Then we have solved our second derivative equal to 0 and found an inflection at 1, 3. We don't need to determine what type of inflection this is. It's just a change in concavity between a maximum and a minimum. Now we have to finish this off and sketch the curve. So there's our information. Here's our curve here. So you can see that we have our maximum at 0.5, our inflection at 1, 3, and our minimum at 2, 1. And you can also see how I have labelled them. Okay, and that's the end of this question. They're quite detailed, these sketching questions. Make sure you're thorough and meticulous and follow the method. Now, stationary inflection occurs when the first and second derivatives are equal to 0. Here's an example. So find and classify the stationary points for y equals x cubed multiplied by 4 minus x in brackets. So we need to differentiate this. We could use the product rule, but it's a bit of overkill. It's much easier just to expand that out and then do term by term. So let's do that. So expanding it, y equals 4x cubed minus x to the power of 4. Differentiate, I get 12x squared minus 4x cubed. Factorise and put it equal to 0. So our solution is x equals 0 or 3. But remember, we need the stationary points, so we need to find the y coordinates, substitute back into the curve. When x is 0, y is 0. And when x is 3, I'm going to get 27 multiplied by 1, which is 27. So we've got stationary points at 0, 0 and 3, 27. Now we need to say what type they are, so we're going to go to our second derivative. Second derivative is 24x minus 12x squared. Substitute in x equals 0. So when I put 0 in here, I'm going to get our second derivative is equal to 0. And have a look what I'm writing here. At x equals 0, the second derivative equals 0, and therefore it is a possible stationary inflection. Remember, a stationary inflection has to have both derivatives equal to 0, and this does have it. But there are limitations to this, which I'm going to go over in the next slide. So we're just going to write possible at this point. At x equals 3, second derivative is equal to 72, take away 108, which is negative 36, which is less than 0, therefore it's a maximum. Okay, so we've got a definite maximum here and a possible stationary inflection here. So there are odd occasions when the second derivative test doesn't work, and here's one of them. Find and classify the turning points of y equals 2x to the 4th minus 5. So we start as we have done and do the first derivative, that is 8x cubed. Put it equal to 0 and solve it, I get x equals 0. We of course want the turning point, so we substitute back in here. Putting 0 in, I get negative 5. So our stationary point is at 0, negative 5. Let's do the second derivative to try and find its nature. Second derivative is 24x squared. Substitute the 0 in, and we get second derivative is equal to 0, which suggests a stationary inflection. But in this case it isn't, it's actually a minimum. There's the curve. So our second derivative doesn't work. It tends to happen with curves where we've got an x to the power of 4 and we don't have any other x's, but it's not the only time. So that's why every time we get first and second derivative equal to 0, like here, that I say it's a possible stationary inflection. And one way to have a look at whether this is to either draw the graph or to plot points on either side, or we can use the first derivative test, which I'm going to teach you now. Now, the first derivative test is more complicated than the second derivative test, and for that reason we always tend to just use the second derivative test unless we end up in this situation. There's one other time when we might use the first derivative test though, and that's if it is just too algebraically difficult to find the second derivative. You know, if it's going to take you 2 pages to find the second derivative, this is going to be much easier. All we have to do here though is test the first derivative on either side and draw a rough sketch. So there's our first derivative there. We know that the critical point is x equals 0, so I'm going to test either side. And just like before, I'm just going to test the sign. So when I put negative 1 into here, I get a negative. We know that that's 0. And when I put positive 1 in, I get a positive. And we just draw a sketch. There's a negative slope. Here's 0. Here's positive. It's a minimum. So you can see how this works, just a rough sketch. This is sometimes called the bucket test as well. So therefore the turning point is a minimum. So for this reason, if the second derivative turns out to be 0, it's a possible stationary inflection. Use your first derivative test to make sure that it is. So let's look at how we might sketch the derivatives. You might be given a question like this, where we're given a random curve and we have to graph or sketch the first derivative and the second derivative. And what we're interested in with the first derivative is it increasing, stationary, or decreasing? And you don't have to be super accurate with this. All you've got to do is do a rough sketch, and they're looking for the shape and position of the curve. So as we go up here, it's increasing, so that's positive. Here it's stationary, so that is 0. Draw a dot there. Here it's decreasing, so it's negative. Here it's also stationary, so that's going to be a dot on the line there. And here it's increasing, so this part here is going to be positive. So we've just got to draw some sort of curve that goes through here and up through there. So that would be the first derivative. Let's have a look at it. Yeah, we didn't do too badly. Okay, that would be perfectly acceptable. Let's just get rid of that so that we can see the other one. So now suppose we want to do the second derivative. Now we're talking about concavity, and we're still going back to this original curve. Okay, so this part here is concave down, so that means it's going to be negative. Here's the change in concavity roughly here, so it'll be 0. And then we have concave up, this part here, and so that's going to be positive. All right, just drawing something rough through there that looks like that's going to be a straight line. It's negative, comes through positive. It's meant to be a straight line. My apologies. Something like that. Let's see how we went. Okay, a little bit steeper, but again, the angle's not that important. It's more important that you get the position right, which we did, and the negative and positive. So that's how we draw the first and second derivative. Now, what if we've got to go the other way? Here we've got the graph of the derivative, and now we want to draw the curve. So we've got to draw a possible sketch of y equals f of x. Now this is harder. Okay, you kind of got to think backwards in your head. So we're not really concerned about concavity. That would be if we wanted to draw the second derivative. Here we've got to go back to the original curve. We've got to think about what has made this curve happen, if that makes any sense. Now this point here would have been a maximum or a minimum, or it's a turning point. So it's either like that or that. Ditto here, because this is when the first derivative is equal to 0. Okay, down here the whole thing's negative, which means the curve's going downwards. Okay, it's decreasing. Up here it's positive, which means the curve was increasing at that point, and that's the same over here. All right, do you reckon we can decipher this at all? Let's have a look at it. So I've got some sort of increasing curve here going up to either a minimum or a maximum. It has to go up to a maximum, doesn't it? So let's get rid of that minimum. So I've got, it's going up, it's going to turn around, and then it's going to go down until it gets to here, and then it's going to turn around. It's going to be a minimum here. Let's get rid of that guy, and then it's going to go up again. Do you think you could draw it? Doesn't really matter where it is. So we're going to go up like this and turn, and then we're going to come all the way down here, whoops, and turn, and then go up. So something like that. Now what you'll learn when we do integration later on is that this curve could move up or down and it'd still be an antiderivative, okay, the opposite of differentiation. So it could be up here or down here, it doesn't matter. So when you ask a question like this, you're looking for something that's increasing. It's got to have a turning point here. It's going to decrease. It's got to have a turning point here, and that's got to go up again. Okay, we're going to move on to the next section. In this section, we're going to be looking at the study of kinematics in one dimension, which is going to involve motion problems of displacement, velocity, and acceleration. So here's an example of a particle moving along a line. It starts at 1, moves to the right until it reaches 5, then turns, and then goes until -3, turns again, and then heads off to the right. Now displacement is like distance, except it has direction. So with distance it can't be negative. Can't say I'm -3 meters away from the window, but with displacement we could. It's typically negative or positive distance away from the origin, but it could also be north or south or east or west. So if an object moves along a line, its displacement from the origin can be written as a function of time. So we use the letter S for displacement, and you can see how I've written that as a function of time, so S of t. If S of t is greater than 0, then the object is to the right of the origin. If it is less than 0, then it's to the left of the origin. Now velocity is the same as speed, except it's also got direction. We can find the average velocity of a particle. We would just do the change in displacement over the change in time. Remember, this symbol, delta, means change. But we're more interested in the instantaneous velocity. What's the velocity at that instant? And that's like the gradient of the tangent. So it's the first derivative. So here's our definition. The velocity at time t is equal to the first derivative of displacement. And there's our definition of our derivative from first principles. If the velocity is greater than 0, the particle is moving to the right. It is increasing. If the velocity is less than 0, the particle is moving to the left. It is decreasing. And then finally, acceleration. We could talk about average acceleration, just like we did with velocity, but instantaneous acceleration is usually what we want. It's the derivative of velocity, or the second derivative of displacement. That's what's written here. So A of t is equal to V dashed of t, or S double dashed of t. Now, if A of t is greater than 0 and the velocity is greater than 0, then the particle is speeding up. However, if the acceleration is greater than 0 and the velocity is less than 0, then the particle is slowing down in a negative direction. You need to probably practice a few of these to understand it. I'll do the other definitions and we'll have a chat about it. If the acceleration is less than 0 and velocity is greater than 0, then the particle is slowing down in a positive direction. And if the velocity is less than 0, then the particle is speeding up in a negative direction. Having a look at those, if the signs are the same, then the particle will be speeding up, and you've just got to see which direction it's going in. So acceleration greater than 0, velocity greater than 0, the particle is speeding up in a positive direction. Acceleration less than 0, velocity less than 0, speeding up in a negative direction. But if the signs are different, then the particle will be slowing down, and then you look to the velocity to see which direction it's going in. You'll need to practice this a bit to understand it. Here's an example. A particle moves along an axis according to the function S of t equals t cubed minus 6t squared plus 9t plus 1. S is the displacement from the origin in centimetres and t is the time in seconds. Usually these questions start with this question. Where is the particle initially? Now they won't say that this is t equals 0. You have to know that. So initial time usually starts in these experiments from 0. All we've got to do is put 0 in here. So 0, 0, 0 is going to be 1. So S of 0 is equal to 1 centimetre. That's 1 centimetre to the right of the origin. B. In which direction is the particle first heading? So for that we need to know the velocity. If the velocity is positive, it's going to the right. If the velocity is negative, it's going to the left. Here's our velocity. It is the first derivative, so we've just got to differentiate. It's 3t squared minus 12t plus 9. And first heading means t equals 0. So put 0 in, 0 in. It means that the velocity at time 0 is 9 meters per second, and that means it's heading to the right. C. When does it turn around? Now I didn't mention this before, but when the velocity is equal to 0, we have a turning point. It makes sense, doesn't it? Because it's the first derivative, velocity. So if we take the first derivative and put it equal to 0, we get the turning points. So it's going to turn around when velocity is 0. So let's put our first derivative equal to 0. we need to factorise that. I'm actually going to take this common factor out that I can see first of all. So divide by 3, divide by 3, divide by 3 gives me this, and now factorise. Gives me that. We've got two turning points, one at 3 and one at 1. So t is equal to 1 or 3 seconds. Now, always look back to the question with this particular sort of question when you get this answer, because normally when we were doing curve sketching, we always wanted to know the y coordinate. Remember that? In this case, we may or may not. Having a look back here, it says when does it turn around, so that's time. So we actually know that. It doesn't say where does it turn around. So we actually don't need to put it back into the curve to find its position. That's the answer. One other thing I want to say here is that if you ended up with a negative, say -1 and 3, you would disregard the -1 because time can't be negative. In this case, we're going to keep both of them though because they're both positive. D, what is the particle's minimum acceleration? First thing we want to do is actually find the acceleration. So we're going to differentiate velocity. I've got the velocity expression up here, so it's going to be 6t take away 12. Now remember, time is going to be always positive. So it's going to start with 0 and then keep going. So we want to know when this is going to be the smallest that it can possibly be. And the smallest will actually happen at when t is 0. It'll wipe that out and we'll get -12. So the minimum acceleration is -12 meters per second squared. And E, describe the particle's motion at t equals 4. So what we want to do here is find the velocity and the acceleration, say in which direction it's moving and if it's accelerating or decelerating. So here's v of 4, it ends up equaling 9 meters per second. So it's going in a positive direction. Here's acceleration at time equals 4. It's equal to 12 meters per second squared. And so that means it's going to be accelerating because both of these are positive. So we're going to get the particle is heading to the right. It has a velocity of 9 meters per second and is accelerating. There are many examples in real life where a quantity varies with respect to time or another variable. There's a couple of them. Height can vary with time. Volume of air or water if you're pumping up something or you're draining a pool. Profit or cost is a common one. Bacteria will change with respect to time, temperature, and radioactivity. Here's an example. A radioactive substance decays in proportion to the weight of the substance remaining. So what on earth does that mean? Okay, well let's have a look how we interpret it and then we'll see whether we can make sense of it. So this dW dt means the rate of decay. Okay, so this is how much the weight is changing as time changes. This means is proportional to, and W is the weight. So it says that weight, W is the weight in grams and T is the time in minutes. So the rate of decay is proportional to the weight of the substance itself. Now we can change that and rewrite it like this. So is proportional means a linear relationship, and actually if we graphed it, it would look like this and go through 0, 0. So this would be, I'm just going to do W dash rather than writing dW dt, and this here would be W. So that's a proportional relationship. We call that direct proportion. So the two things are in direct proportion to one another. As one goes up, the other goes up. So that's why we can rewrite it as this. This is actually a straight line down here. So pretend it's y is equal to kx. It's a straight line, isn't it? Through 0. In this case, k is called the constant of proportionality. Part A. Show that the equation W equals 35 e to the kt satisfies the formula dW dt equals kW. So what we've got to do here is differentiate this and then try and make it look like that. Okay, well, let's do the derivative of this to begin with. All right, we know that this e to the kt is going to stay as e to the kt, and then we're going to multiply by the derivative of this second function. So the 35 hangs around, e to the kt stays the same, and then we multiply by the derivative of kt. Now k is just a constant there, it's a number, like 2. If we were doing the derivative of 2t, we would just end up with the 2. Can you see why I've got the k kept? Now we're going to make it look like this. Okay, we're nearly there. See, I've got the k, I want to make that into w. It actually is w, can you see? So this is w times k, or kw. There's one last thing I want to say about this. We've got a relationship here where the derivative is equal to the thing itself. E is the only thing that when you do the derivative, you get what you had. Okay, I know there's an extra constant in here, so we've got something at the front, but sine won't work, cos won't work. No other function will give you something that looks almost identical to itself, except for E. B. What is the initial weight of the substance? So again, that means time equals naught. So we just substitute in t equals 0. So W of 0 is equal to 35 e to the naught. E to the naught, of course, is 1, so our initial weight is 35 grams. After 3 minutes, the weight of the substance is 22 grams. Find the value of K. So these questions always go like this. They'll ask you the initial weight, and then they'll give you a pair of values and ask you to find the constant. Be careful here. This is W, and this is T. So when we substitute it in, the 22 goes there, because that's W. Okay, we're going to have to solve this using logs, but before we do that, let's divide both sides by 35. Now we're going to take logs of both sides, just like this. You might want to unpack that and just put that into log form straight away. That's okay. I tend to teach it this way because it's really easy. So we're going to get ln of 22 over 35. Ln e to the 3k, the 3k comes down, and ln e is just 1. So I end up with 3k equals that. And so once I divide by the 3 and put that in the calculator, I get negative 0.155. And I write that to 3 significant figures. D. Predict the weight of a substance after 10 minutes. Okay, we're just going to substitute in t equals 10. Now, of course, I know what k is. There it is. And I just put in the calculator. It's okay to leave that as 3 significant figures. It's probably better to put more, but usually with the IB they will mark both correct, especially if you write your working out. So after 10 minutes it's 7.43 grams. And then finally, at what time is the substance expected to drop below 10% of its initial weight? Its initial weight is 35. 10% of its initial weight is 3.5. So we could go 3.5 equals 35 e to the blah blah blah. But then I'm going to just write this up so you can see it. So I could go 3.5 equals 35 and then all the rest of it. And then I would divide this under here. But that's actually just 10%, isn't it? This part here. So I can actually just write it like this. That's 10% there. You can do it this way if you want to. So 10% is 0.1 is equal to e to the negative 0.155 t, and I want to solve that for t. So take logs of both sides again. In this case, I've decided to do it just into log form. So ln of 0.1, and if I take ln of this side, the negative 0.155 t comes down the front, and I get ln e, which is just 1. So see how I got that? And then divide by negative 0.155 in the calculator, and I get 14.9 minutes. You don't need to change that into minutes and seconds. So just 3 significant figures. One last thing to say here. Another common question here is they want to know the half-life of things. That means when it's at 50%. So you can actually just put 50% in here. You can do it the other way if you like. In that case, you do 35 here. Half of that is 17.5, and then solve it normally. Do it whichever way you get it right. Okay, whatever makes sense to you. Okay, last section. There are different methods we can use to find an optimal solution to a problem. We could create a function and then graph it and find the maximum or minimum point. we could use formulae such as the vertex formula if it was a parabola and then find the turning point. Or we can use calculus to find when the gradient of the tangent is 0. So here's a really common example, and it's probably one you might have been given in junior school as well. It's called the volume of a box problem. Given a piece of A4 paper and it's folded into a box that looks like this, and the corners are cut out to a particular height. So when it's folded into the box, we have got a height of x. Down here, which is this distance here, we've got 29.7 take away x, take away x. So this is 29.7 take 2x, and the width of the box would be 21 take away 2x. Now one way to solve it is just to set up a spreadsheet. You put in the various heights and put in a formula for the length. That would be that 29.7 take 2 times this value here. Same for the width. Multiply the 3 together to give the volume. And what we can see when we graph it, we've got sort of a parabola looking thing, and it seems that the maximum volume is going to be when the height, or x, is equal to 4. Now if we were to do it algebraically, all we have to do is find algebraic expressions for the length and the width of the box, which we did earlier. So the length is 29.7 take 2x, the width is 21 take away 2x, and our volume would be this. Now we can't use a vertex formula to find the minimum or maximum because it's not a parabola. This is actually a cubic. So we'll have to find other methods to solve it. So we could use a graphical method. We could graph that expression and then just find this turning point by looking at it. And again, it looks like 4 is the solution that gives us the maximum volume. Let's have a look at how we might do this on the graphics calculator, because it is possible you get a question like this on the calculator paper. So we're going to enter our volume formula into the graph section and then hit draw. Now you are going to need to adjust your viewing window. It's unlikely that you'd see a graph. So a couple of tips here with these sorts of questions. Set the minimum x as 0 and the minimum y as 0 because it's unlikely they'd be negative. We can't have a negative volume, for instance. The other little trick is to try and make this y value, the max for y, very large. Remember we had quite large volumes. So push this out to around 2000 or something. I've also made that a little bit bigger as well. When we draw it, I can see the graph, so I can go gsolve then max, and lo and behold, we get the maximum occurring at 4.04, which is just slightly above 4. Now, one of the easier ways, I think, to do this question is actually through calculus. There's a little bit of algebra in it. We're going to differentiate this function. So I've got v is equal to x, outside of brackets 21 minus 2x, and then new brackets 29.7 take 2x. Okay, firstly I'm going to expand the x into here. That's going to give me that. And now I'm going to do FOIL on this and expand it all out. Once it's tidied up, I get this 4x cubed minus 101.4x squared plus 623.7x. Okay, seems like we've done a lot of work. We haven't done anything yet. We need to differentiate it, put it equal to 0, and then solve it. So here's dvdx. It is 3 comes down, 12x squared minus 2 times 101.4x plus 623.7. Okay, there it is there. We need to put that equal to 0 now. And so I'm not going to try and even factorize that. It looks too ugly. Let's go straight into the quadratic formula. So putting it in, got a bit of a mess. Go through on your calculator and put this in with a plus there. Work it all out and then go and edit back and change it to a minus. It's the quickest way to do it. So I get 4.04 and 12.9. Now we have to justify with calculus that this is a maximum. So second derivative is 24x minus 202.8. Substitute in x equals 4.04. At x equals 4.04, our second derivative is 24 times 4.04 minus 202.8 is negative 105.84, which is less than 0, therefore concave down, therefore a maximum. So the volume is maximised when a height of 4.04 centimetres is chosen.